Center of mass is the next topic. We will work with a two variable function, which we're gonna denote with the lowercase Greek letter rho. So this is rho. It looks like a P, but it isn't a P. So this is the lower case Greek rho. And it denotes density. The density as in physics, how much mass there is per units of either length, area, or volume. Right now we're gonna do area. So rho is gonna be a function of X and Y, and we're gonna have varying density depending on where we are on the piece of lamina. We're gonna assume we have a piece of lamina for which we're gonna find the center of mass. So this is the density. At X, Y point. And for density, we want to use kilograms. So we're going to use the kilograms per square meter. Square meter. So those are going to be the units for rho. They could be different depending on what we are measuring. But for now, we're going to assume that rho, the density, is going to be kilograms per square meter, which can be lighter or heavier depending on where we are. This is similar as the regular f of x. Yeah, so we're going to be doing double integrals where rho is going to be integrated, and that is like a function f of xy, except that we're not going to call it f of xy. We're going to call it rho of xy because we want to determine density. So f is typically reserved for a height in 3 dimensions, so going up or down, while rho is not necessarily a height because we're going to have a flat lamina. So if you have some kind of flat lamina, pretend this is a 2-dimensional flat lamina. So this lamina may be perhaps heavier here and lighter there, and then maybe not so heavy here. So we have different densities depending on where we are on the lamina, but the lamina is going to be flat. It is not going to be particularly it is not going to be uniform density, although I guess we could do problems with uniform density. Those are the ones we did in calculus 2. Now we're going to address problems where the density is not uniform. Yeah, so the difference, let me put a different kind of shape. So when we are talking about rho, this is a 2-dimensional rectangle, this rho, whoops, I'm almost put a P rho, there you go, tells us that this is going to be perhaps heavier here and lighter there, and maybe not as heavy there, medium, and maybe heavier again here, even heavier, etc. So rho tells us how heavy. Oh, I shouldn't use heavy because heavy is measured as a unit of force. Heavy has to do with force, and we're dealing with mass. Although there is if we include gravity, then there's a relationship between something being more massive and heavy. But technically speaking, we should say that this is more massive at some points than others. As opposed to thinking, even if we have the same function, but we call it something else, f, then we're thinking of a height. Then we have some kind of height. Now, the height here, it corresponds to perhaps the massiveness of the same point here. So we could have exactly the same function, say x squared plus, I don't know, I'm just making this up, sine of y, just to give an example. And this could also be x squared plus sine of y. So in this context, so even though we have the same function, the same expression for the function, and even though we have perhaps the same domain, in this context, f would represent some kind of height and some surface, while rho represents how heavy something, again, I'm using heavy, how massive something is here on this plate. So this is an actual plate that may be more massive in some places than others. Another way to say that is more heavy, although that is technically not correct because heavy is how we measure, or it's an adjective we use for force, not for mass. Let's do an example. Okay, so assume that rho, the density of x, y, is x squared plus y squared. We want to find the center of mass of a plate, a rectangular plate that is center, well, one vertex is center at the origin, 2 units one way, and then 1 unit up. And we want to find the center of mass of this plate, assuming that the plate has this kind of density. So what that means is that if you plug in 0, 0 here, the weight per square meter will be 0. So it's weightless here. Again, I keep using weightless even though it should be mass. There's no mass here. But as soon as you move off a little bit of the origin, then you start having more and more mass. And then the farther away you go, the more mass you will have. So the maximum mass will happen here simply because both x and y are contributing in a positive way to the addition of the mass. So, or the other way to think of it, if you take a square root, which is a one-to-one function, then you end up with the distance of the point xy to the origin. So the farther away, the larger this number will be, even with the square root. So the density at this point will be 5 because 2 squared and 1 squared will be 5. So that is the density. The density here is 0. 5 kilograms per square meter. The density here at 1, 1 will be 2. Yeah, because 1 squared plus 1 squared is 2. And then 1. Down here, the density is also 1. Yep. So this goes by circles because of the way this particular. There's a density of 1 here on this quarter of a circle. There's a density of 1 here. This is not. Two. Oh, I lied. Why is it 2 here? Let me just double check. 1. Oh, this 2 is not the density. I lied about this 2. This is 2, 0. 1, 0. There we go. The density here is 4. There we go. Because we have 2 squared and 0 squared. 2 squared and 0 squared. The density here will be, yes, 1. There we go. The density is 0 there. This point is 0, 1, and the density is 1. There we go. Now we got, yeah, now we're good. So this is a circle, and then the circle corresponding to a density 4 is not going to run through the 2 because that is less density. So that's kind of circles. Yeah, we have a constant density on circles. Anyway, so the way we start is we find the mass. Mass is going to be denoted with m, mass. And mass is going to be the double integral of the density with respect to the area over the region. And the region is, of course, this. In this example 1. So the mass is equal to the integral from 0 to 2 on the x's, from 0 to 1 on the y's, of the density, which is x squared plus y squared, dy dx. So while we are integrating with respect to y, x is a constant, 0 to 2. So we have x squared is a constant, so x squared y plus y cubed over 3 as we plug in y from 0 to 1. And then after we do that, then we still have to find the integral of that with respect to x from 0 to 2. Let's continue on a new page. So that is equal, this integral is equal to the integral from 0 to 2. We're going to plug in 1 for y. So that is going to be simply x squared plus 1/3. And when we plug in 0, we're going to obtain 0. Make sure you do get 0 when you plug in 0. Dx. So that is going to be x cubed over 3 plus 1/3 of x from 0 to 2. So 8/3 plus 2/3. 0 is going to yield 0, so we end up with 10/3. So that is the mass. And the units are kilograms. Let's go back to y. The density is in kilograms over meters squared. But then we're multiplying by units of meters and meters. So these are meters and so on. So y is meter, is a length. That's meters and meters. So when we multiply with the meters cancel off because here we're dividing by m squared. And so we end up with kilograms. So the mass is in kilograms. All right. So now we find the moment from the y axis. So how is this mass? What we're going to do is we're going to multiply this density, which provides the mass, by the distance from the y-axis. So that we're going to end up with some kind of weighted average. The farther we are, the more weight, and as far as averaging, the more weight we're going to put on that mass. The closer we are, the less weight we're going to put on that mass as we try to find some kind of average. So farther away, we're going to give that mass more importance because the number we're going to multiply with is going to be larger than with numbers that are closer to the y-axis. That's how we figure out the moment. So we have the same double integral, x squared plus y squared dy dx. Y is going from 0 to 1, x is going from 0 to 2. But we got to multiply by the distance. So this is just the same mass. If we multiply by the distance from the y-axis, that means we have to multiply with x. So x provides distance from the y-axis. Note, x is distance from y-axis. See, if you have a point here and you want to know how far you are from the y-axis, you look at the x because you go x, y. So we are multiplying by x. X is going to contribute to this integral, and that's how we obtain the mass with respect to the y-axis. So of course we're going to end up with x cubed. When we integrate that, we're going to have x cubed y plus xy squared. When we integrate that with respect to y, we're going to have xy cubed over 3 from 0 to 1, because we're still integrating with respect to y. We're finishing that integral. So that is 1 for the y's, from y equals 0 to 1. So at 0, we're going to end up with 0. At 1, we're going to end up with x cubed plus x over 3 with respect to x. That's going to give us x to the 4 over 4. When we plug in 2, we get 2 to the 4 over 4 plus x squared over 2 in addition to the 3 plus 2 squared over 6. That is going to give us 16 over 4 is 4 plus 4 over 6 is the same thing as 2/3. Three times 4 is 12 and 2, 14 over 3. So we end up with 14 over 3 for the moment with respect of the plate with respect to the y-axis. Now we figure out the moment of the plate with respect to the x-axis. This is kind of weird because the letters kind of crisscrossed. You know, moment with respect to y multiplied by x. Now we're going to do moment with respect to x, so multiply by y. 0, 2, 0, 1, y, x squared plus y squared dy dx. And we're going to obtain a different number. So the mass is 10 over 13 over 3. The moment with respect to the y-axis is 14 over 3. By the way, the units are going to be, okay, so this was kilograms over meters squared, but then we multiply by those 2 meters. So we end up with kilograms, but then we multiply back by another length. So that's going to give us kilograms times meters. I'm not going to try to figure out what that is, because when we find the actual coordinates, we got to divide this by the mass. So the kilograms are going to simplify, and we're going to end up with pure meters. So we're integrating with respect to y. Y x squared is going to give us an integral from 0 to 2 of y squared over 2, or x squared, y squared over 2, plus, then we have y cubed, which we're going to integrate, y to the 4 over 4 from 0 to 1 on the y's dx. So we still have the integral from 0 to 2. 1 is going to give us x squared over 2. 1 is going to give us a fourth 0 is going to give us 0 and 0. So we have x cubed over 3, but we're going to plug in 2. 8 over 6 plus, well, a fourth times x, but plug in 2 over 4. And then when we plug in 0 into those two, we're going to end up with 0 anyhow. So that is 4/3 plus 1/2. That's 11/6. 8, 3 is 11, common denominator is 6. All right, so what is the center of mass? Oops. Is equal to, well, typically it is x bar, y bar. In this case, the way we find x bar is the moment from the y axis, which is here, 14 over 3, divided by the mass, 10 over 3, comma, the moment with respect to the x-axis, which we just found, 11 over 6, over the same mass, 10 over 3. And then we simplify, of course. We have to simplify. So that is going to give us 7 over 5, comma, the 6 and the 3 simplify, so we still have a 2, 11 over 20. Okay, when you finish, try to make sense of this. And what I mean by that is make sure your answer is not a crazy answer. It's not something that is total weird. For example, if the point is outside the plate, you gotta be suspicious. Sometimes when the plate curves, yes, we see that the center of mass may be outside. So like if you have a horseshoe, the center of mass is not gonna be on the horseshoe itself. It is gonna be outside. So if you have a washer, again, the center of mass will not be on the washer, will be outside the washer and the hole. In this case, though, the center of mass, because everything is pretty, there's no gaps in this plate, we expect this to be inside. So 7 fifths is 1.4. So if this is 1.4 would be a little farther to the right. So that would be where the x value of the center of mass is. 11 over 20 is just a little above the center, going up. So if this is the center, just a little bit above it. Okay, that's where the center of mass. Farther to the right and a little bit above where the actual center of the plate is. That's a good thing, because as we analyze this density, we notice that the plate is going to be it will have much more mass on this corner, and that pulls the center of mass in that direction, as opposed to in the center of the plate. Also, the center of mass is gonna be pulled up, but not by much, because the difference between those two is not too great. The difference between 2 and 5 is huge, and that's why we have to move 0.4 units this way. But the difference between 4 and 5, or 1 and 2, is not as great, and that's why we just move about 0.05 meters up to get to the center of mass. So after you find centers of mass, make sure your answer makes sense, that you don't have some kind of crazy answer. Let's do a second example. Okay, the density will be the same. But now we're going to cut. We're gonna have a different plate. We're gonna take the original plate we had, and we're gonna cut it diagonally this way. So we're gonna go 2 units, 1 unit, origin. So 2, 0, 0, 1, 0, 0. I'm gonna piggyback on this. So the mass is gonna be 4 in this corner, 1 on this corner, 1 again here in the middle, 0 there. So the mass is gonna be quite heavy here. There's no mass of 5 because that was cut off. So pretend you take this, take a saw and cut this off. Where is the new center of mass? We don't know. That is to be determined. First, we have to find the mass. It will be naive, in this case, to think that the mass will simply be half of the mass we found here. So the mass here is 10/3. Half of that would be 5/3. It would be naive to think that this is 5/3 in mass because the mass of the whole plate was, yes, 10/3. So you're thinking, well, half it, and you get half of the mass. No, 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 no. Because the plate is heavier on that corner than on this corner. So when even though we cut in half, more of the mass is going to be gone and less of the mass is going to be retained here. So what we know using common sense is that the mass is going to be, of this is going to be less than 5/3. If we get 5/3, based on this example, example 1, if we get 5/3, which is half of 10/3, or more, there's something wrong. Yeah, and always use common sense when in academia. We should know the equation of this line, which is kind of easy to figure. The y equals, the slope, of course, is negative because we go down. It is a half because we drop 1 when we run 2. Drop of 1, run 2, x. And the y-intercept is 1 plus 1. So there we have it. Okay, so that is going to be useful. And we don't have a rectangle. By that, what I mean is that the variables, the x and the y within the region we're integrating over, is not going to be fixed numbers. The boundaries are not fixed numbers. Okay, so the mass, let's set this up, is the integral from 0 to 2 as before. And on the y's, we're going to go from 0, yes, but we're not going to go to 1. It's for each column, we're going to stop here. For each partition, we're going to stop on this boundary. So where we stop is a y value of negative half x plus 1. Negative half x plus 1. We're still going to integrate x squared plus y squared, which is the density dy dx. So we're still computing the mass, just the beginning. Okay, so this is 0, 2. We're integrating with respect to y. So we're going to have x squared y. We're going to plug in this upper limit, and we're going to plug in 0. So when we plug in the upper limit, we get negative 1/2 x plus 1. And that's it. So that is the integral of x squared dy from 0 to that limit. But then we got to add, okay, y. After we integrate, we're going to end up with y cubed over 3. We're going to plug in this for y and 0. So that is negative 1/2 x plus 1 cubed over 3 dx. So I'm skipping a few steps. As long as we can do that in our head, I don't see too much. But make sure you do it in your head. As soon as you start writing things on paper, then write that as side work, please. Okay. Let's not skip too much, though. So we have negative x cubed over 2. I'm distributing the x squared plus x squared. And I'm going to start, I'm going to close this, split this into two integrals. And I'm going to start integrating this guy. I'm going to pull out the 1/3. We can, when we integrate this with respect to x, we can set this to be u. So by applying u, we're going to end up with u to the 4 over 4. So we have negative half x plus 1, which is the u to the 4 over 4, over 4 from 0 to 2 on the axis. But there is more to it. If I assume that this is u, du will be negative 1/2 dx. And so because we want to substitute the dx, this is from calculus 1, we need to multiply by -2. So there's an extra -2 showing up in there. And again, I'm applying to go from here to here, I'm doing u substitution. This is reasonably straightforward, so I don't necessarily have to write all of the particular steps of what u is. As long as we are correct, though, we multiply by -2 to compensate for having a u, then I think we're okay. And we're going to plug in 2 and 0. While that is cooking, we are moving this. We have, of course, negative x to the 4 over 8 plus x cubed over 3 from 0 to 2. Now let's come back to this. Let's put a negative. Let's simplify the numbers, the coefficients, 1 over 6. Now, the next thing is important. Plug in the 2 for x. So we have negative 1/2 times 2, negative 1, plus 1, we're going to end up with 0 to the 4. Now, many times when we have a polynomial, when we plug in 0, we're going to end up with 0. This is, however, not a polynomial. At least it is not written as a polynomial. And plugging 0 will not give us 0 here. Think about it. If x is 0, yes, this vanishes, but then we still have a 1. So we have to subtract 1 to the 4. So this is interesting. We do not get 0 when we plug in 0. Many times I go through problems and I say, oh, it's 0. Yes, but even if I don't write it down, I'm still taking a few seconds to, in my head, plug in the 0 to make sure we actually get 0 or we don't get 0. So even if it's not written, you have to take the time to do that. Otherwise, you're going to end up with inaccurate results. Okay, so that is going to be 16 over 8. That is -2. 0 gives us 0. 8 over 3 plus 8 over 3. And then we have a double negative plus 1 over 6. Let's change everything to sixths. Because that is the greatest common denominator. So that is -12 over 6 plus 16 over 6 plus 1 over 6. And that gives us 5 over 6 for the mass. 5 over 6. The mass of the whole rectangle, according to example 1, is 10 over 3. Half of that would be 5 over 3. So 5 over 6 is even half of that. So isn't that interesting? If you split the original region according to this density, if you go and split this way, this is going to be a quarter of the total mass. The mass of this triangle is going to be exactly a quarter of the mass of the whole rectangle, and that upper triangle will be 3/4, which makes sense because this is the rectangle is way more dense on the upper right corner than in the lower left corner. And so it makes sense that 3/4 to 1/4 ratio for how we distribute the density among those two triangles. Okay, so now I'm happy. I'm satisfied because we get something that is even smaller than 5/3. Now we gotta find the moment with respect to the y-axis. So we have a double integral. We still have x squared plus y squared dy dx. We multiply by x. So, and the limits are going to be the same, from 0 to negative 1/2 x plus 1, from 0 to 2. Okay, so we have x cubed when we multiply times y, and we're going to be plugging y, this upper limit for y and 0. So we have x cubed times x squared is x cubed, the y of the integral, negative half x plus 1. Okay. Plus x times y squared. We're integrating with respect to y. So we're going to have x times y cubed over 3, but then we're going to plug in this. So we have x times negative half x plus 1 cubed over 3. Close this parenthesis that I started back here. All of that with respect to x. Okay. This is more complicated than the previous integral. In this case, sometimes adding the x or the y complicates things. Sometimes they don't. Sometimes actually they could help. The point I want to make though is when we were finding the mass, we could make this u and things would work out reasonably well. Here, I guess you could make this u, but then there's this extra x to deal with. So the u substitution does not work as smoothly as one would expect. Instead, what I'm going to do is just FOIL this out and then go with it instead of making a u substitution. So we're actually going to simplify this. When you are doing your integrals, do one way or the other, or maybe a third way. There's more than one way to evaluate the integrals. Whichever way you use, though, do not use a graphing calculator or some kind of technology of that caliber or higher to obtain the results. So let's simplify this. We're going to end up with negative x cubed over 2 plus, oh, I meant to the 4 because we have an extra x here, plus x cubed. Plus, I'm going to factor the x over 3, and then we're going to FOIL this out. I'm going to let you do that on your notes. Make sure you practice how to do that. Negative 1 over 8 x cubed is the first term, plus 3 over 4 x squared minus 3 over 2 x plus 1. Close parenthesis, and I have to do, or close the, well, I still have to close the bracket. Let's see if I can close it here. And then we should include the differential. So this is not very good notation, but I'm putting dx and an arrow indicating there is a dx that should show here. 0, 2, negative x to the 4 over 2 plus x cubed minus x to the 4 over 24. So those two are going to combine in the next term, in the next step rather, plus, oh, the 3's will cancel out nicely, x cubed over 4. Again, those two are going to combine, minus the 3's simplify, so we have x squared over 2, plus x over 3 when we multiply x over 3 with the 1. We're going to close the bracket, dx. So next, we're going to simplify the polynomial before we actually go and integrate the polynomial. So this is going to be equal to 0 to parenthesis. Those two will combine. This is 12 24ths, and this is 1 over 24, and they're both negative. So we end up with negative 13 over 24, x to the 4. Those two combine. We have 1 1/4, so that is 5/4 plus 5 over 4 x cubed. So those 4 terms are taken care of. Then we have minus x squared over 2 plus x over 3, close parenthesis, dx. So we got negative 13 over 24 times, we're going to end up with x to the 5 over 5, 2 to the 5 over 5, especially because we got 0 when we plug in 0, plus 5 over 4 times 2 to the 4 over 4, minus, well, let's write down a half, 2 cubed over 3, plus 1/3, 2 squared over 2. When we plug in 0, we're going to end up with 0 because we have a nice polynomial going here. So 24 has 3 2's. 2 times 2 times 2 is 8. Actually, has more 2's. No, 8 times 3 is 24, so only 3 2's. So 3 2's simplify. We end up with 2 2's still left over, times 13, that's 26, 52. So we have negative 52 over, and then we still have a 3 times 5, 15, plus 2 to the 4 is 16, 4 times 4 is 16, so we still have a 5, minus 1 2 simplifies, so we end up with 4 over 3, plus 1 2 simplifies, so we end up with 2/3. Well, the common denominator has to be 15, negative 52 over 15 plus 75 over 15. That's really negative 2/3 combined. So we multiply by 5, negative 10 over 15. So 75 minus 62. 75 minus 62, 13/15. Okay, so that is the mass with respect to the y-axis. Now we have to do another integral for the mass with respect to the x-axis. And that's the way it is. We just have to go through those integrals. So the mass with respect to the x-axis will be the double integral from 0 to 2, from 0 to negative half x plus 1, x squared plus y squared. This time we multiply by y, the distance from the x-axis, dy dx. Okay, so when we put the y into x squared, well, rather when we multiply, we have x squared y, integrate x squared y squared over 2. We're going to plug that in. X squared negative half x plus 1 squared over 2. That takes care of this term. Now y cubed, when we integrate with respect to y, will give us y to the 4 over 4. We're going to plug in those two. So plus negative half x plus 1 to the 4 over 4. Wow. Now, this x squared messes things up. I cannot use the u substitution. If we do, we still have to deal with the x squared, and that can complicate things. So I'm not going to do that. I'm going to actually FOIL that out. So this is the integral from 0 to 2. Let's put the x squared over 2 outside of, well, we FOIL this out. So we have 1/4 x squared minus x plus 1. So you have to FOIL that out, FOIL, FOIL, to make sure we get this. Dx. I'm going to split this into two integrals. And the reason is because here we may use the u substitution. There's no extra x outside that would mess that up. We have to deal with the 1/4, but that's easy. You just factor it out. So when we use u substitution, all of this would be u, and we end up with that quantity, negative 1/2 x plus 1 to the 5, but then we have to divide by 5. I'm going to put the other 5 as a denominator of a new fraction. So this is really u to the 5 over 5. The 4 was already pulled out. But in order to use u substitution, u equals negative 1/2 x plus 1, du would be negative 1/2 dx. So we multiply both sides by -2 to leave the dx alone. And that way we can actually substitute the dx, -2. And we will evaluate that from 0 to 2. Now watch out. If you plug in 0, you're not going to get 0. You get 0 when you plug in 2. So we got to be careful in this expression. All right. So we have two things cooking. We go back and forth from one to the other. So this is going to be 1 over 8, multiplying the 2 and the 4, x to the 4. But we're going to integrate. So we really have x to the 5 over 5. 2 to the 5 over 5, because we're plugging in the 2. Minus x cubed, x cubed over 2. Let's put the 1 over 2 outside, and I'm dealing with x cubed. So the integral of that will be x to the 4 over 4 plus just the x squared, 1 times x squared over 2. So we're really integrating that, 1/2, and we're going to end up with 2 cubed over 3. Plus, simplify those numbers, and we end up with negative 1 over 10, because that is 20, and 2 up there, that makes 10. Plug in the 2, and we get 0 to the 5 into this expression. Minus, plug in the 0, and we end up with 1 to the 5. 3 2's simplify, so we end up with 4 over 5 minus 3 2's simplify, so that is 2, plus 1 2 simplifies, 4/3. Double negative makes a plus 1/10. Common denominator of those fractions will be 30. So multiply this by 6, 24/30. Multiply that by 30 minus 60/30, plus multiply that by 10, 40/30, and multiply that by 1. Okay. 65, when we add the positive fraction, 65/30. Oh, I lied here. We do need to multiply this by 3. There we go. Now we're good. 24, 64, those two together over 30. 67/30, but then we're going to take away 60. So we end up with finally 7/30. Okay. So now we are ready to write the final answer. Center of mass, also denoted by x bar, y bar, is equal to the moment with respect to the y-axis over the mass, the moment with respect to the x-axis over the mass. So we have fractions. The moment with respect to the y-axis is 13/15. The moment with respect to the x-axis, we just found it to be 7/30. The mass is in a even previous page. The mass is 5/6. And now we go ahead and simplify. Start simplifying. So this is 13 times 6, the outer, and then the inner 15 times 5, comma, 7 times 6 over 30 times 5. I'm running out of ink, and it always happens in the worst moment. So let's simplify. A 3 and a 3 cancels off from the 15 and the 6. So we still have a 2 times 13 is 26 over, and then the 2 5s remain over 25. So this is a little more than 1, comma. The 6 and the 30 simplify down to 5 in the denominator. 5 times 5 is 25, 7/25. So this is the center of mass. Does it make sense? Oh, that's not the plate. The plate is this one, this triangle. So where's this point in here? Well, this is 0, 0. This is 2, 0. And this is 0, 1. And 1 will be here in the middle somewhere. So we got to go past 1, but just a little bit. 1/25 is 0.04. So 1.04, just a little bit to the right. That's where, that's where we're going to be on the x-axis. Now, it is interesting because if this was a uniform density, this side would be way heavier than this one because there's much more to it. But this is not uniform density. Remember, the density here is 4 kilograms per square meter. Here, the density is only 1. So, and the density here is 0, density here is 1. I believe maybe here the density will be higher. I would have to check. But let's assume that it is about 1 in all of this, which is not true on the edges. So the density would be about 1 here or less than 1. And here, the density is for sure more than 1. So it makes sense that this area is smaller and yet this line balances out. So the line that I'm dotting is not 1, that is just my reference. The dotted line is actually at 26 over 25. 7 over 25 is a little more than a quarter, I think. So if we split this into half and half, a little above it, and where those 2 points, those dotted lines intersect, that is where we have the center of mass. And again, it looks like it shouldn't, the center of mass, if this was uniform, would be about a third and about a third this way. So it would be somewhere in this. We have to move it to the right because we have much more mass on this side versus on this side. So there it is. Center of mass with density that is not uniform.